Good morning, everybody. So we start, you remember we were talking about the quantitative relations of the MOS capacitor. Okay, so let's have a look at some numbers. You remember that in the theory of the capacitor, we have the ratio between the equilibrium minority current concentration NP0 and the equilibrium majority current concentration PP0. If we take the typical values like a dopant concentration equal to 10 to the 16th, and we consider the room temperature case, we have for the intrinsic concentration 10 to the 10th electrons per cubic centimeter, corresponding to NP0 equal to 10 to the 4th. So as anticipated, the factor exponential of -2 UF is very small. The one that is in the expressions coming from the solution of the Poisson equation. The threshold of the strong inversion, you remember it is the condition in which the surface potential phi s is equal to 2 phi f. With these numbers, it is equal to 0.72 volts. In normalized units, it is about 27 or 28 normalized units. We already encountered the permittivity of silicon. Permittivity of silicon, as you remember, is equal to the relative permittivity, that is 11.7, times the permittivity of vacuum, that is 8.854 10 to the -14 Farad per centimeter. Now, putting all these things together, we can calculate the Debye length for the holes. That also appears in the solution of the Poisson equation, and it is quite small. It's a fraction of a micron, as you can see. In the calculations, we at some point found out the function f. You remember this function f is rather complicated. Here you have f squared, okay? And we found out that the charge per unit area of the semiconductor, QSC, is proportional to F. So what is the coefficient? Can we give the coefficient in front of F? Meaning this coefficient is 2 times the permittivity KT over QLA. Obviously, since F is a pure number, all these factors multiplying F is consistent with QSC, so it is a charge per unit area. And of course, it is equal to the value taken by QSC when F is equal to 1. So we can call this quantity F of 1. We shall see it in a second. Here. So we define QSC up 1 as this coefficient, okay? So it is possible to normalize this coefficient, to use this coefficient as a normalization factor when we want to describe the charges, okay? So in this figure is probably not in the book, but you can find it in the website. We can draw a graph in which, using the normalized potential US as an abscissa, we can draw a graph of the different contributions to the total charge of the semiconductor in normalized form. So the continuous line here is due to the electrons. You see immediately, we are, of course, in a log scale. Okay, so you see immediately that in the accumulation condition, which corresponds to negative values of US, the contribution of the electrons is negligible. Okay. Then when we are in the range in which US is positive, the contribution of the electrons grows exponentially because it is a straight line with a positive slope, okay? But in any case, the contribution of the electrons is still smaller than that of the holes, that is the dashed line, okay? And of that of the bulk charge associated to the dopant concentration. Only when we reach this point, you remember the normalized value of 2 times phi f is about 27, okay? This vertical line corresponds to 27. So this is the threshold of the strong inversion, and the other vertical line corresponds to UF, and it is the boundary between depletion on the left and weak inversion on the right. Okay. So when we reach the strong inversion and we go a little beyond strong inversion, then you see that the contribution of the electrons becomes dominant with respect to that of the bulk charge and of the holes. This is a replica of a figure that we already commented. It is the normalized charge in the MOS capacitor. You remember that we calculated the capacitance per unit area of the MOS capacitor. And we found that it is the series of two capacitances. One is the oxide capacitance per unit area that is constant. And the other one is the capacitance per unit area of the semiconductor. The latter is called CSC, and its definition is shown in the first line. There is a double sign because we must choose a sign depending on whether we have a positive value of the surface potential or a negative value. Okay, so that this capacitance is always positive. So since the capacitance is the series, that means the inverse of the total capacitance is equal to inverse of the oxide capacitance plus the inverse of the semiconductor capacitance. The normalized capacitance C over Cox is equal to this function, okay? And we can immediately express, it is an easy calculation, we can immediately express CSC as a function of F or as a function of US because F depends on US. So the calculation is boring because we have this function F that is not so easy to deal with, but numerically it is very easy calculation. So we can draw a graph in which we represent the capacitance of the MOS structure as a function of the surface potential. And this is what we find. We find that when the applied voltage, UG is the normalized applied voltage, so it is the VG times Q over KT. And UFB on the horizontal axis is, of course, the normalized flat band voltage. So when we apply a gate potential that is very large or very negative, the total capacitance of the MOS structure is equal to the oxide capacitance, because you see that the ratio C over Cox asymptotically tends to 1 to the right and to the left. In the intermediate region near the origin, the series is smaller than the limiting values because the semiconductor capacitance also has an influence to the total. These are two curves because they correspond to different values of a parameter, and this parameter R is a pure number that is the ratio of two lengths. You can see it here. R is the semiconductor permittivity times the thickness of the oxide divided by the insulator permittivity times the Debye length. So it is a pure number that is given by this ratio of two geometrical parameters and some physical parameters. Of course, we should in principle repeat all the analysis for the N-substrate MOS capacitor, but it is intuitive that the analysis is just a replica of that of the p-type substrate. Okay, so it is just a dual situation, so we don't do it. And the relation between the charge in the semiconductor and the surface potential for the n-type substrate is just the same as that of the p-type substrate. It is simply mirrored from left to right. So in this case, we have accumulation on the right that is a positive surface potential, because accumulation for the n-type substrate means that we have an excess of electrons near the surface. If we go to the left of the origin, we have the portion of the curve that is qualitatively of the type of the square root type, and this corresponds to the depletion and weak inversion conditions. Then we reach near the value -2, we reach the threshold of strong inversion, and then when we keep increasing the modulus of the surface potential, we have the strong inversion condition. Strong inversion for the n-type substrate means that we have a layer of holes near the surface. So at this point, we have enough information to start considering the MOS transistor. The MOS transistor, as you know very well, is the most important device at present in the integrated circuit technology. And this figure shows a schematic view of the cross-section of the device. We start from a p-type substrate, which we assume to be uniformly doped, okay, with some concentration of acceptor atoms. Then we grow the silicon dioxide on top of it. It is the gray rectangle here. So this is the insulator, the gate insulator region. On top of it, we deposit the gate contact. So we have one contact G here. On the two sides of the gate oxide, we diffuse two N+ regions, that are two regions of the N-type that are heavily doped. And you know, diffusion is isotropic. So the diffusion proceeds not only in the vertical direction, but also in the lateral direction. So the N+ region goes under the gate, both on the right side and on the left side. Okay. And this is important for the correct functioning of the device. Then we deposit two contacts on the two diffused regions. The contacts are called drain, the one on the right, and source on the left. Okay. And finally, we have the bulk contact below. Okay. The two N+ regions in the modern technology are obtained by another process that is called ion implantation, okay? But after ion implantation, it is necessary to perform a short diffusion process. So in any case, we have a diffusion following ion implantation. So we have these lateral diffusions anyhow. Of course, we have a device in which there are 4 independent contacts. So we have 3 independent voltages. In the analysis of the device, it is preferable to consider the bulk contact as the reference contact. So the 3 independent voltages that are used in the analysis are VSB, that is the voltage applied between source and bulk, VDB, that is the voltage between drain and bulk, and VGB, that is the voltage between gate and bulk. Okay. The voltages applied to the source and drain with respect to the bulk in this type of device, that is a device with the P substrate, these 2 voltages can never be negative, because if you apply a negative voltage to the source with respect to the bulk, you bias the PN junction between bulk and source in the forward condition. So you have a lot of current flowing from the bulk into the source, and you don't want it, okay? It would be wrong to do such a thing. And the same on the other side, okay? So the source to bulk voltages and the drain to bulk voltages must be either 0 or positive. That is, the 2 junctions between source and bulk or drain and bulk must be at equilibrium or in the reverse bias condition. So there will be, if they are in the reverse bias condition, there will be some current, but very small, flowing through the junctions. Another observation is this. This device, in contrast to the bipolar device, okay, this device is symmetric from left to right because the geometry is symmetric, and also the 2 dopants distributions of the source and drain regions are equal to each other. So in principle, there is no structural possibility to distinguish between source and drain because they are symmetric. The only way to distinguish between them is the applied voltage. So in the normal functioning of the device, the drain voltage with respect to the bulk is different from the source voltage with respect to the bulk. And the contact whose voltage is higher in this device is the drain contact. So as you see in the inset on the left, we have the condition VDB non-negative. That means that the drain junction should never go in forward bias. VSB never negative, because the source junction as well should never go in direct bias, sorry. And finally, VDS larger or equal to 0 because we must distinguish between source and drain. Obviously, the device is 3-dimensional, but we assume that the device is uniform in the direction normal to the page. and that the width of the device in the direction normal to the page is equal to some value that we call W. W is the so-called channel width. Other important geometrical aspects are these. You see the symbol LG on top. LG indicates the geometrical length of the channel or the gate region, okay? Instead, we have two important points in the device. One point is the point in which the PN junction, that is you see this line is the line in which we have the PN junction, where the dopant is prevailing of the N-type above and of the P-type below. So this line indicates the boundary of the PN junction of the source on the source side. This boundary intercepts the interface between semiconductor and oxide at this position. This position is taken as the origin of the reference, and we take the x-axis, as we usually do, oriented from the interface to the bulk. And then we take the y-axis, you see it here, horizontally, starting from the origin placed, as we said before, in this point. On the other side, we have another point in which the drain junction here intercepts the interface, okay? So the distance between this point and the origin is marked with L. L is the channel length. It's called the channel length of the device, okay? Or better, it is the electric channel length of the device, because we also define LG. LG is the geometrical channel length. But the important one is the electric channel length, that is the distance between those 2 points. Now, assume that the gate contact is biased with respect to the bulk contact with the voltage that is positive and large. How much? Well, you can observe that if you start from the gate metal, you have metal followed by insulator followed by semiconductor. So if you look at it vertically, you have an MOS structure, okay? So we can repeat can use some of the concepts that we already met for the MOS capacitor. And we imagine that the gate to bulk voltage, VGB, is large enough to produce the condition of strong inversion of the interface. So we have a layer of electrons, and this layer is the thin gray region along the channel, okay? So this gray region in this figure, as you can see, connects the N-type region of the source to the N-type region of the drain. So we have two regions that are lateral, that are rich of electrons. And we also have a region in between that is rich of electrons because we have the inverted layer. And this inverted layer bridges the two N plus regions. So it produces a connection, an electrical connection between these two regions. So it is intuitive that if we apply a voltage from drain to source, such that the drain voltage is larger than the source voltage, we shall have a current flowing, entering the drain, crossing the intermediate region under the gate. This region, you know, it is called the channel of the MOS transistor, and this current will go out through the source contact. Okay, so the channel creates a bridge between source and drain and closes the electric loop and allows for the current of the channel. How much current do we expect? Essentially, it depends on how much charge we have in the inverted layer. Okay, if we have many electrons in the inverted layer, okay, the channel will be less resistive qualitatively. So we shall expect a larger current in the channel. If there are not so many electrons in the channel, we expect a smaller current. But how is the amount of electrons in the channel established? It depends on the value of the gate voltage. If the gate voltage becomes more positive, we attract more electrons in the channel, so the channel will be less resistive, and we have a larger current, and vice versa. So this is the typical functioning of a valve, that is a device by which, acting on the gate to bulk voltage, we control the current flowing between the drain and source contact. Okay, so controlling the voltage at one port, that is the gate port, we control the current in another port, that is the source drain port. Okay, and this is the perfect, or the most perfect, type of valve, because of course there is no current flowing through the gate, because there is the gate insulator in between. So the control port, the gate to bulk port, is able to control the current in the device without absorbing any power, because there is no power flowing into the gate, because there is no gate current. The gate current is zero, so the power in the gate port is also zero. Okay, so this device is called N-channel MOSFET. You know very well that MOSFET, MOS, means metal oxide semiconductor. FET means field effect transistor. Field effect because essentially the amount of charge in the channel is controlled by the voltage. Transistor also, you remember, is a short for transfer resistor. Transistor means transfer resistor. Before we move on, we make another comment. The two source and drain junction are biased in reverse. So they have a depleted region, as usual we indicate with Ln and Lp the extension of the depleted region on the N side and on the P side of the junction, okay? On the other hand, since we have a condition of inversion of the surface in the channel, we also have a depleted region. You remember, there is a depleted region in which the contribution, the main contribution to the charge density is due to the dopants, and then we have the surface in which we have the electron layer. So the depleted region has a width, and we cannot call LP this width because the symbol LP has been already used up in the junction. So from now on, when necessary, the extension of the depleted region under the gate will be called XD instead of being called LP as we did before. Finally, we consider an elementary strip that is indicated here with thickness dy, okay? This elementary strip is made of metal oxide semiconductor, okay? So qualitatively, it is like an MOS capacitor of infinitesimal width, okay? In principle, it is not, because you remember the MOS capacitor that we have considered so far is a really one-dimensional device. In this case, the infinitesimal strip is not actually one-dimensional because when the transistor operates, there is also a lateral current flowing through the elementary strip, okay, from in the horizontal direction that corresponds to the y-axis. So it is not really one-dimensional, but almost, as we shall see later. Okay, so this elementary strip will come of use later on when we develop the analysis of the MOS transistor. Now, the purpose is to calculate the current. That is, we want to calculate the current flowing from drain to source depending on the voltages. So we expect that in this device there is only one current, the current that flows into the drain through the channel and goes out of the source. We know already that there is no current through the gate because of the insulator. In principle, there is some little current through the bulk contact because the two junctions are reverse biased. So there is the saturation current of the two junctions does exist, but it is very small. So we neglect the saturation current of the two junctions, and we assume that there is also no current through the bulk contact. So there is one and only one current from drain to source. On the other hand, there are three independent voltages, VDB, VGB, and VSB. Okay, and these three voltages can be controlled independently. So we expect that the analysis will be able to bring us a function in which one current, the drain current, for instance, is expressed as a function of three voltages. This slide shows the starting point of the calculation. First of all, we assume that the device is uniform in the direction normal to the page, that is the direction of the z-axis. Okay, so you see here there is no dependence on the z-coordinate. Then hypothesis number 2, we assume that we are in the steady state condition. Okay, so no dependence on time. Hypothesis number 3, we assume that at each position in the channel, so at each point y between 0 and L, the channel is in the strong inversion condition. So we have a concentration of electrons corresponding to strong inversion, okay? When that happens, we say that the channel is well-formed. A condition of well-formed channel means strong inversion everywhere in the channel. We don't know how to do it formally, but qualitatively, we may say, if we apply a gate voltage large enough with respect to the bulk contact, then we expect that the channel will be well formed. Okay, so for the moment, we apply a voltage. In this case, it is indicated with VGS, so a voltage between gate and source, but we shall see it is the same thing, okay? Large enough means larger than some limiting value that we call VT. VT is also called a threshold voltage. We don't know how to calculate the threshold voltage, but we shall do it later. And the condition VGS larger or equal than VT implies a well-formed channel. At this point, we have a two-dimensional structure, so we expect that the electron current density Jn and also the hole current density Jp in principle have two components. So Jn is equal to some coefficient times I. I is the unit vector of the x-axis plus the component along the y-axis times j, that is the small j, is the unit vector of the y-axis. And similarly, we have jp equal to jpxi plus jpyj. Okay, but immediately after, we notice that the current densities along the x-axis cannot exist because there is the insulator in between. So no flux of electrons or holes in the vertical direction is possible. So we eliminate immediately two of the components, those along x. Okay, so Jnx and Jpx are 0. Another observation is the following. If we have a well-formed channel, that means that we have a lot of electrons and very few holes. So we expect that the contribution to the total current density coming from the electrons will be dominant with respect to that coming from the holes. So we neglect the contribution of the holes. So eventually, out of all these components, only one component survives because J and X and JPX are 0. J and Y is much, much larger in modulus with respect to JPY, okay? So this device, in essence, is of the type that is called unipolar, because the current density is essentially due only to one type of carriers. In this example, the electrons, because we have an N-channel MOS transistor. So this is a fundamental difference with respect to the bipolar transistor, in which, as you remember, we had to consider both electrons and holes to correctly describe the functioning of the device. In this case, we have a unipolar device. That means that at the very end, the total current density, that in general is equal to the sum Jn plus Jp, in practice is equal only to Jn. And this Jn has only one component, that is the horizontal component. So it can be written as a scalar function, Jny, that still depends on x and y, times the unit vector of the y-axis, okay? The property of being unipolar is fundamental because if J, the total J, is equal to Jn, that means that the divergence of J must be equal to the divergence of Jn, because the two vectors are equal to each other. But we are in a steady state condition, okay? So you remember the continuity equation for the global set of charges and currents, okay? So the continuity equation that derives from the Maxwell equation states that the time derivative of the charge density plus the divergence of the total J is equal to 0. We are in a steady state condition, so the time derivative of the charge density is 0. So we are left with divergence of J equal to 0. But as we said before, J is equal to Jn. So that implies that the divergence of Jn is also equal to 0, which means that the recombination is 0. You remember, in general, the continuity equation for the electrons in steady state, we have that divergence of Jn is equal to Q times the net recombination rate U. But if the divergence of Jn is 0, then U is 0. That means vector Jn is solenoidal. Vector Jn is solenoidal. What does it mean? It means that the flux of Jn does not depend on the position. So here it is a little bit difficult to express this concept in words, because it would be much, much preferable to have the blackboard, okay? But I'll steal one more minute to complete the concept. Imagine a surface that is normal to the page and vertical. For instance, a surface that leaves a trace like this vertical line here in the figure, okay? Assume that you are calculating the flux of the current density across this surface, okay? If the current density is solenoidal, it means that this flux is the same wherever you place the surface. So instead of here, you may place the surface here, or to the right, or in the middle, okay? The flux of Jn across it is just the same everywhere in the channel. That means that we can calculate the current of the channel by simply calculating the flux of the current density at any position y in the channel. Okay, so we now go back for a second to the other page. The flux of Jn is, of course, the projection of Jn along the y direction, integrated along x, that is in the vertical direction, and along z, that is in the direction normal to the page. In particular, z goes along the width of the channel, that is from z equal to 0 to w. Y goes from the interface x equal to 0 to infinity, that is to the bulk. This is the current in the channel, and it does not change if we change the position of this integrating surface. So it is a constant everywhere in the channel. We shall come back to this in 10 minutes. So we shall start at 10:13. We stop now. Okay, so we start again. You remember we have expressed the current as this integral. We use the general symbol I for the current. We did not specify yet whether this current is entering the drain or entering the source. We'll do it later. Now we have to calculate this double integral, but of course, since there is no dependence on the z coordinate, the integral with respect to z is simply multiplication by w. So we see immediately that the drain current, the MOSFET, is proportional to the width of the channel, as everybody knows. Also, considering the expression of Jn is a scalar called J and Y times the unit vector of the y-axis. But then we have another scalar multiplication by J, so we obtained a scalar, okay? So essentially, now we have to calculate a single integral with respect to x of the horizontal component of the current density of the electrons. Now we exploit the expression of the current density. You remember, in general, in the semiconductor mathematical model, the current density is expressed with the drift diffusion terms, okay, is the sum of the drift and diffusion terms. However, at some point in the analysis of the mathematical model for semiconductors, we introduced another form of the current density that we call the monomial form, that comes essentially from a change in the variables, okay? Instead of using the standard variables of the semiconductor model, we introduced new variables that are the so-called quasi-Fermi potentials, phi n and phi p. In this case, we need only the quasi-Fermi potential phi n for the electrons, because we are considering the electron current density. So the monomial form of the current density is written here. It is Jn equal to minus Q times the mobility mu n times the concentration of the electrons times the gradient of phi n. Phi n is the quasi-Fermi potential for the electrons, okay? So that is the general expression of the current density. But at this point, we remember that this current density has only one component. That is the component along the y direction, okay? So the component along the y direction is simply J and Y equal to minus Q, the mobility, n times the component of the gradient along y, that is the derivative of phi n with respect to y. This is the expression of J and Y that we need in the integral. The other component, that is the component along x, formally can be written, okay? Of course, it is equal to minus Q mu n times the derivative of the quasi-Fermi potential with respect to x. But this component is zero, because we already observed that there is the insulator, so this current cannot cross the insulator, so it must be equal to zero. On the other hand, here we have a product of factors, okay? And the other factors like mu n and n are non-zero because we are in the channel, so the concentration of the electrons in the channel is large. For sure, it is not equal to zero. And the mobility is a parameter, so it is a non-zero parameter, and of course Q is non-zero. So the only possibility for this product to be zero is that this derivative, the phi n over the x, is zero, okay? On the other hand, if this derivative is equal to zero, then that means that phi n does not depend on x. So the only possibility left is that phi n depends only on y, okay? So we have that it is useless to continue to use the symbol of partial derivative, because at this point we have understood that the quasi-Fermi potential depends only on y. So we use the standard symbol of derivative, and then we replace the expression of j and y into the integral. On the other hand, the integral is carried out with respect to x. And since the factor d phi n over dy does not depend on x, because phi n does not depend on x, we can extract this factor from the integral. So we find a somewhat simpler expression of the current, that is W times the derivative of phi n with respect to y times the integral of minus q mu n over dx. And this integral must be carried out from the infinity into the bulk. Okay. Now we introduce another simplification. And this simplification is that when we integrate over x, it is useless to continue the integration in the neutral region. We can limit the integration in a region near the channel, because we are calculating a current that flows horizontally near the surface. So there is no current flowing from source to drain in the bulk, okay? So instead of carrying out the integration along x between 0 and infinity, that is to the bulk, we do it between 0 and xd. So the first step is we replace the upper limit of the integral with xd. We notice that in the integral, in principle, n depends on everything, x and y. Okay, there is no reason for n not to depend on x or y. And in principle, also the other factor, the mobility, may depend on x and y. Okay, so when we calculate this integral, since we saturate the x coordinate, eventually we expect that this integral will depend on y. Now we introduce a normalization. Number one, we observe that the integral of minus Qn dx that we must calculate is nothing else than the inversion charge per unit area. We have already introduced this concept in the MOS capacitor. In this case, this integral has the same meaning, that is charge of the inversion layer per unit charge, per unit area. However, it depends on the position in the channel where we calculate it. Okay, so this is different from the current density. The current density is a solenoidal vector, so its flux does not depend on the position y. But in this case, this integral does depend on the position y. Okay. Now, we introduce an average mobility that we call mu of the electrons, mu sub e. And the definition of it is the integral between 0 and xd of minus q mu n over x divided by the integral of minus qn dx. Observe that the numerator of this fraction is exactly the integral that we must calculate here for the current, okay? The denominator of this fraction is exactly the charge per unit area of the inversion layer. So in essence, when we calculate this integral, what we do is we multiply and divide this integral by Qi, by the charge per unit area of the inversion layer. In the division, we obtain the average mobility. Obviously, this is an average mobility because if you cancel minus Q, you have an integral of mu n weighted with the concentration of the electrons divided by a normalizing factor that is again the concentration of the electrons. So we divide by Qi to obtain this average mobility, and then we multiply by Qi. So this is a manipulation that provides us with an alternative expression of the current. At this point, you notice that this current is a constant. That means it does not depend on the position of the channel in which we calculate it. You remember, the current density is solenoidal, so the current is the same at each position in the channel. But on the other hand, we see that W is a constant. Mu E is some function of y that is always positive. Qi is the charge density of electrons, so it is always negative. So in this product, this factor, of course, is a constant, so it never changes sign. This factor mu is always positive, it never changes sign. Qi is always negative, so it never changes sign, and the product must be a constant. We don't know yet whether the constant is positive or negative, but in any case, if the product is a constant, also the other remaining factor can never change the sign. Okay, because it is embedded in a product that is invariant in which all other factors do not change sign. Conclusion, this derivative, the phi n over the y, is either always positive or always negative. Okay, so phi n is a monotonic function of y. Being so, phi n is invertible. That means that from the function phi n of y, whatever it is, we don't know it yet, we can extract the inverse function y of phi n. Okay, assume that we did it. So that means that the y in the mobility and the y here can be replaced with the function of phi n. But if we do so, the conclusion is that this equation is a separable equation. It is a differential equation that becomes separable. Why? Because we can bring dy to the right. So we have that the left-hand side depends only on y. The right-hand side is w d phi n times a function of phi n times another function of phi n. Okay, so this equation, by this trick of inverting phi n of y, becomes separable. After the separation, then we can integrate over the channel both sides of the equation. So the left-hand side is I dy, and we integrate it over the channel, meaning that y goes from 0 to L. L is the electric channel length that we already introduced. On the other hand, I is a constant. So as a consequence, this integral provides L times I. The integral on the right must be integrated with respect to phi n. So it is W, that is a constant, times the integral of mu e, that depends on phi n, times qi, that depends on phi n, integrated with respect to phi n, between some value that we don't know yet, that is phi n at the left end of the channel, that is corresponding to y equal to 0, to phi n of y equal to L. Okay? Now it is possible to simplify somehow the calculation, because we assume that the mobility, the average mobility, depends on the position along the channel. But if we take a closer look at it, we see that this is not true, because you remember that we analyzed the so-called sources of the mobility degradation. Okay, and we found out in this analysis that mobility depends on temperature, on the dopant concentration, and if we are in a near a surface, okay, depends also on the interaction with the interface, with the surface. Okay, so we can analyze these three aspects. Okay, mobility depends on temperature, but this device has the same temperature at each position. There is no reason why the temperature should be different from one point of the channel to another. So the temperature is constant with respect to position. So there is no dependence on position of the mobility due to temperature. Number two, the concentration of the dopant also is a constant. everywhere because we are assuming a uniform dopant concentration. So there is no reason why the mobility should depend on position because of the dopant. Then there is the effect of the interface, okay? You remember that the macroscopic model for the effect of the interface of mobility considers the normal component of the electric field, okay? Qualitatively, you can think that at some position of the channel, the normal component of the electric field is equal to the voltage drop across the oxide divided by the thickness of the insulator. This gives you the field in the insulator, okay? And then you remember, we analyzed this in the MOS structure, the field in the insulator is proportional to the field at the surface of the semiconductor, okay? And the proportionality factor is the ratio of the permittivity of the insulator and the permittivity of the semiconductor, okay? So the question is this: is the vertical component of the field inside the insulator the same at each position of the channel, or does it change when we move from one position to the channel to another? And the answer is, in this condition, that is when the channel is well formed, the vertical component of the field is practically constant at each position. And the reason is that in the strong inversion condition, the surface potential is substantially equal to 2 phi f. It does not change too much with respect to this value. And of course, the gate voltage on the gate is constant everywhere in the channel. It is Vg prime, okay? So the vertical component of the oxide field is constant along the channel, is practically constant. So also this mechanism of degradation of mobility has no dependence on position along the channel. In conclusion, we can take the mobility equal to a constant, the average mobility equal to a constant. So we now simplify the expression of the current, as you can see in the middle of the page. It is I equal to the ratio W over L times the mobility times the integral of the inversion charge per unit area integrated over phi n along the channel, okay? Now we change the variable again. Why? Because it is more convenient to consider, instead of the quasi-Fermi potential, to consider the surface potential. We already defined the surface potential in the MOS capacitor. It is the potential at x equal to 0. Here we define the surface potential in the MOS transistor exactly in the same form, but here the potential is two-dimensional because it depends on x and y in general inside the device, okay? So when we fix the position of the surface, x equal to 0, the corresponding surface potential still depends on the position y along the channel. So we have phi s depends on y. On the other hand, also the quasi-Fermi potential depends on y. So we have two functions that depends on the same variable. So we can eliminate y and we can think of expressing phi n as a function of phi s, or vice versa, phi s as a function of phi n. So we now change the variable in the integral. Okay, so by this trick, we change the variable. So we express qi as a function of phi s instead of phi n. But in so doing, we must modify the differential. So the phi n becomes, obviously, d phi n over d phi s times d phi s. So we must be able to also to calculate this derivative now. If we succeed in doing this, then the integral will be carried out over phi s. So we must also change the integration variables. And we shall go between phi s at 0, that is at the beginning of the channel, to phi s at L, that is at the end of the channel. Okay. This calculation is not easy in general, but it becomes easy if we are in the strong inversion condition. That is, if the channel is well formed everywhere at each position y. So in order to make the calculation of this integral easy, we introduce an approximation or a set of approximations. And to do so, we go back to the figure. Here. You remember the figure. At some point, we introduce this elementary strip, okay? And this elementary strip starts from the metal, which is followed by the insulator, which is followed by the semiconductor. And in the semiconductor, we have an inversion layer, a depleted region, and a neutral region. Okay. To calculate the current, we have to perform an integration over the horizontal coordinate y. So over a number of strips like this. Okay. So the approximations that we take, one is obvious. We consider that since the channel is has a strong inversion condition, we consider that we have an inverted layer followed by a depleted region. Okay, so the approximation is that in the depleted region we assume full depletion, and then we assume the so-called Ashe approximation. The Ashe approximation, you remember, means abrupt space charge edge. That means that we go from a fully depleted region, a region in which the only contribution to the charge density is due to the dopant, to the neutral region with a discontinuity here, okay? And the final approximation, that is something new, because this was not necessary in the MOS capacitor, is that we treat this elementary strip here that is placed at some position y in the channel as if the elementary strip is an MOS capacitor. So we use the same relation of the MOS capacitor. as I anticipated earlier, this is an approximation because we have a current that flows laterally across this elementary strip. So we have also a field that is horizontal, and this is not present in the true MOS capacitor. So this is the approximation, okay? But in the strong inversion condition of the interface, this approximation works very well. So in conclusion, in the strip, we use the same expression of the inverted charge per unit area that we have in the integral Qi. We use the same expression as that of the MOS capacitor. Okay. So I mentioned the full depletion and Ashe approximation. Then I mentioned the use of the elementary strip of thickness dy as a parallel plate capacitor, that is an MOS capacitor. So these are two hypotheses, okay? Combining the two hypotheses, you remember, we can express the inversion charge Qi as minus Cox VGB prime minus phi s minus gamma phi s. So we are using exactly the same expression as we did in the MOS capacitor. Where is the difference? The difference is that phi s depends on y. But we don't care because we are performing the integration over phi s due to the change in the variable. The integration over y was performed in the left-hand side. It's already done, okay? So phi s depends on y, but it is not appearing in the calculation. It is not finished yet because another consequence of the hypothesis that the channel is fully inverted at each position is that in the current density, the ohmic term is dominant with respect to the diffusive term. This condition is completely different, as you remember, from that we analyzed in the bipolar device, okay? So this condition of ohmic transport is not obvious. It is something that must be demonstrated, okay? We shall do it, but later. However, the important consequence of the property that the transport in strong inversion is essentially ohmic is that we can demonstrate, and we shall do it, that the surface potential at each position in the channel is equal to the quasi-Fermi potential phi n plus a constant, and this constant is the Fermi potential. Okay, so phi s differs from phi n by a constant. This makes life very easy because if phi s is equal to phi n plus a constant, then the derivative of phi n with respect to phi s is equal to 1. Okay, and we need such a derivative here. So using the approximations that we just illustrated, this derivative is equal to 1, and the expression of Qi becomes extremely easy. So the integral can be done very, very easily. This set of approximations together, that is 1 plus 2 plus 3, go under the name of gradual channel approximation, GCA. Okay, so the gradual channel approximation is actually a set of different approximations. The parallel plate capacitor for the elementary strip, full depletion Asch approximation, and ohmic transport corresponding to this. Okay. Conclusion. We must calculate this integral here, in which, you remember, we have Cox, that is a constant factor. So we take Cox out of the integral, and Cox multiplies the other factors that are W over L times mu E. So globally, this common factor will be called beta, okay? And you know very well that beta is, in quotes, the gain of the, or the multiplicative factor of the MOS transistors, okay? So it's W over L mobility times Cox, okay? It is not finished yet because to calculate the integral, we need the integration limits, okay? It is possible to demonstrate, and the demonstration is still based on the assumption number 3, that if we specify this relation phi s equal to phi n plus phi f at the two ends of the channel, first we can manipulate the relation in this form. We subtract phi f and we add phi f, okay? It is possible to demonstrate that at the left end of the channel, that is when y is equal to 0, this difference in parentheses becomes equal to the voltage VSB. So at the left end of the channel, Vs at 0 becomes VSB plus twice the Fermi potential. Similarly, on the right end of the channel, phi s of L becomes equal to the voltage applied to the right contact with respect to the bulk, VDB, again, plus the constant 2 phi f. So we have the limits of the integration. The final thing is that so far we gave the integral a general name I, okay? What we want to calculate is the drain current. That means that we want to calculate the current entering the drain contact, okay? So we want to calculate a current with the assumption that ID enters the drain, okay? Well, if you consider the integral, you find immediately that you have a minus sign that was originally attached to the charge Qi because charge Qi is negative, okay? You bring the minus sign to the left. So you have minus I equal to this integral. This integral is by construction positive. because the quantity in brackets, that is the integrand, is positive. And of the two integration limits, the upper one is larger than the lower one because Vd by construction is larger than Vs. Okay? So the integral is positive. Beta, of course, is positive. Minus I must be positive. We call it ID. And this is the correct definition of the drain current of the MOS transistor. As you may expect, this integral is a function that depends on the gate voltage that is embedded in VGB prime, on the drain voltage that is here in the limit, the upper limit of the integral, and VSB, the source voltage. So as we expected, we have found an expression in integral form, of course, of the drain current that depends on the voltages of the three independent voltages of the device. Of course, there are limitations because this formula applies only if the channel is well formed. So it applies only in the condition of strong inversion of the channel. And this condition is not the only condition that is possible in the MOS transistor, of course. So this is a simplified theory, but it works quite well for many operating conditions of the device. Before continuing, we observe that if we take the difference between VDB and VSB, okay, of course we obtain VDS, that is the voltage that is applied between drain and source. As we anticipated at the very beginning, the calculation of the current of the MOS transistor is better done considering the voltages with respect to the bulk reference. VGB, VDB, VSB. But you remember very well that in the analysis of circuits, it is preferable to refer the voltages to the source contact, VDS, VGS, and VBS, okay? But the transformation is very easy, of course. So at some point later, we shall consider this transformation. Another observation is this. We expect that when we calculate the integral and we find the expression of the drain current in explicit form, this expression will be nonlinear. Obviously, it will be nonlinear with respect to VDB and VSB. It may be linear with respect to VGB, but not with respect to the other voltages, okay? So, in essence, we find a nonlinear expression of the current with respect to the voltages, okay? So, in the circuit theory, when we consider the small signal equivalent circuit of the device, at some point we have to calculate the so-called differential conductances, okay, that are the derivatives of the drain current with respect to the individual voltages VGB, VDB, and VSB. Okay. So we expect that at some point we must calculate the differential conductances. Here there are no capacitances simply because the theory here is in steady state, so there is no reactive effect accounted for. Okay, of course, associated to the two junctions, there are also the capacitances, and they must be introduced at the later stage in the analysis of the circuit if necessary. Okay, so the next point will be the calculation of the differential conductances of the device. We stop here and we shall resume in 10 minutes. Okay, so we conclude this part of the class by considering the integral here that defines the drain current of the MOS transistor. And as you remember, we start defining the conductances. You remember we have a current ID that depends on three independent voltages, VDB, VSB, and VGB. So we have three possible derivatives, okay? Since the relations are non-linear, we must define the differential conductances that are the derivatives of the current with respect to one of the voltages while keeping the other two voltages at a constant value. So we start with the definition of the so-called drain conductance, GD. It is also called output conductance, GO. It is defined as the partial derivative of the current with respect to the VDB voltage, while keeping the source bulk voltage and the gate bulk voltage constant. In the other representation, in which the voltages are referred to the source contact instead of the bulk contact, the drain conductance is defined as the derivative of the drain current with respect to the voltage VDS, that is the difference in the drain and source voltages, while keeping VBS and VGS constant. If you check the two definitions are completely equivalent. Now, the point is that in order to calculate the drain conductance, we should first integrate to find the current, and then take the derivative with respect to VDB in order to find the conductance, okay? But this would be silly, because why should we integrate and then take the derivative? We can do it directly, remembering that the derivative of an integral with respect to the upper integration limit is just the integrand calculated by replacing the variables with the upper integration limit. So the conductance GD is simply found by letting phi s here and there equal to VDB plus 2 phi f. So we do it. And we find this expression of the drain conductance. It is equal to beta VGB prime minus VDB minus 2 phi f minus gamma square root of d VDB plus 2 phi f. On the other hand, you remember that when we defined the integration limits, we also found that VDB plus 2 phi f is just the value of the surface potential at the end of the channel, at y equal to L. So we can use a short notation, and instead of writing VDB plus 2 phi f, we can simply here, for instance, write phi s of L. And similarly here, we can write phi s of L, okay? But remember, inside beta, we have Cox. So if we take out Cox, we are left with W over L average mobility, and then we take out also a minus. So minus Cox times this parenthesis is nothing else than Qi at L, and then we have a minus because we need minus Cox to define the charge, okay? So we see that in this theory, the drain conductance, that is the derivative of the drain current with respect to the drain voltage, is proportional to the value of the charge per unit area at the drain end of the channel, okay? Now we introduce a definition. The definition is that we define the saturation surface potential at the drain as the value of phi s of L that makes this quantity equal to 0. Okay, so this is easily calculated because it is a second-degree algebraic equation. So we calculate which value phi s of L makes this parenthesis equal to 0, and we call it saturation voltage. Okay. Then, remembering that phi s of L is equal to VDB plus 2 phi f, we define the saturation drain voltage with respect to bulk from this relation, phi s of saturation minus 2 phi f. So we simply invert the relation between phi s at the end of the channel and VDB. So this provides us with the saturation voltage at the drain with respect to the bulk. If we instead want the saturation voltage at the drain with respect to the source, we simply subtract VSB and we define VDS of saturation with this formula. Okay, so from the output conductance, we have derived a useful concept, that is the concept of saturation of the MOSFET. We have another useful outcome from the drain conductance, and it is the following. Let's go back to the general expression of GD, this one, okay? And consider the limiting value of GD when VDS goes to 0. Okay, so we simply impose that in this expression, if VDS goes to 0, that means that the difference in voltage between drain and source is 0. That means that the drain voltage with respect to the bulk becomes equal to the source voltage with respect to the bulk. So we simply replace to VDB here and there, we replace VSB. Okay. What happens next? It happens that now we remember that Vg prime is equal to Vg minus Vd flat band. Specifically, Vgb prime, that is the gate to bulk voltage with a prime, is equal to Vgb without the prime minus the flat band voltage. But Vgb minus Vsb is Vgs. At this point, we start referring the voltages not to the bulk contact, but to the source contact, okay? Because automatically from this difference we find VGS. In the square root, well, we can simply say that VSB is equal to minus VBS. It's just the same voltage in reverse. Of course, VSB for the N-channel device is always non-negative. That means that minus VBS is always non-negative. So we don't have any problem in having a minus sign under the square root because VBS in itself is negative. Okay. At this point, we collect all the summands VFB, 2 phi F, gamma. You see, all of them have a minus sign. Okay, so we collect them together in a single symbol that we call VT, that is the threshold voltage. The threshold voltage is V of flat band plus twice the Fermi potential plus gamma square root of 2 phi F minus VBS. Okay. And we use a more compact expression for GD, simply beta times VGS minus VT, okay? Now we can observe that GD, that is the derivative of the drain current with respect to drain voltage, is a conductance. It must be positive. It would be a physical nonsense to have GD negative, okay? So we observe that for these expressions to have a meaning, it must necessarily be that VGS is larger than VT, okay? So this is the condition for which this theory works. And this is also the condition that we expected of a well-formed channel. You remember at the beginning, we said we expect here to find some voltage VT such that when VGS is larger than VT, the theory is applicable, and we call it the threshold. Yes, now we have found it. The threshold is, in this theory, this expression. You observe that it is made of constants because the Fermi level is, Fermi potential is a constant, and also the flat band voltage is a constant. But we have a dependence on the bulk voltage with respect to the source, okay? So the dependence of the threshold voltage on the bulk to source voltage is called the body effect, body effect. And it is something that we don't like, because we would really like that the threshold of the MOS transistor would be a constant, okay? But it is not. It depends on the VBS voltage, okay? So in integrated circuits, this dependence is an inconvenience because of course we have that the threshold of a device depends on the working conditions, okay? So a possible solution is that if we succeed in doing that, is that VBS is constant, is kept constant, which sometimes one succeeds in doing, sometimes he does not. A simple way to make it constant is to make it equal to 0 if possible. So in circuits, if it is possible, but it is not always possible, but if it is possible, in order to avoid the body effect, the source contact is shorted with the bulk contact, if possible in the circuit, okay? So we can come to a provisional conclusion that we have separated two large operating conditions, two important operating conditions. One operating condition is that VGS is larger than the threshold. When that happens, the device is functioning, okay? So there is a current in the channel. Instead, when VGS is smaller than the threshold, in this theory, we say that the device is off. The MOS transistor is not working. Actually, you know, it is not true. We simply have a smaller current in the channel, and this current is called the sub-threshold current. So still there is a current, okay? But in this simplified theory, we simply state if the voltage between gate and source is smaller than the threshold, the device is not functioning. The current is equal to 0. In the above threshold condition, we also distinguish two regions. One region is when the VDS voltage is positive but smaller than the saturation voltage. As you know, we call this the linear region, okay? And in the linear region, this theory applies, okay? So this is essentially the current of the linear region. Of course, it is not a linear function of the voltages, but it is called the current of the linear region, okay? If we increase the drain voltage beyond the saturation value, we enter another functioning region that is called the saturation region, in which the theory that we have outlined so far is not applicable, okay, is not applicable. Now we are in the position of calculating the current. We simply calculate the integral. The integral is made of essentially three pieces. One piece is the one that comes from VGB prime. The other comes from minus phi s, and the other comes from the square root of phi s, okay? So the term that comes from VGB prime is very simple. It is the integral of a constant. So if you calculate it, and then you have VGB prime times the difference of the integration limits, okay? And this difference, of course, is VDS. Then you multiply by beta. It is not shown here, but we'll do it later. So this is the first ingredient. It is called the linear part of the characteristic because it depends linearly on VDS. Then we have the part that comes from phi s, from this one, okay? So when you integrate, you have 1/2 phi s squared, which must then be limited between the upper limit and the lower limit. So you have this block, apart from the beta, gives you 1/2 VDB plus 2 phi f squared minus VSB plus 2 phi f squared. When you explicitly do the calculation, you find that many pieces cancel each other. For instance, 2 phi f squared cancels 2 phi f squared here, okay? Then we turn from the voltages referred to the bulk contact to the voltages referred to the source contact. So VSB is already okay. VDB is called VDS plus VSB. So when we do this calculation, we have more cancellations, okay? So at the very end, the term we are talking about, that is called the quadratic term because there is VDS squared, okay, gives this block. But then we have to consider the original piece, okay, that we calculated earlier. So we have the original piece minus this piece, okay? So when we put them together, we have still more cancellations, sorry. So we have eventually a linear part with respect to VDS and a quadratic part with respect to VDS. So this part of the model will eventually be multiplied by beta and will provide the so-called linear parabolic part of the model. Linear parabolic because there is one part that is linear with respect to VDS and the other one is quadratic. Instead, the dependence on VGS is linear, okay? And there is no dependence so far from or on VBS, okay? To conclude, we must calculate the part of the current associated with the square root of phi s. Obviously, the integral will give you 2/3 gamma times phi s to the 3/2, still limited between the two integration limits. So here there is nothing to simplify, okay? We must take it as is. So we have 2/3 VDB plus 2 phi f, that is the upper limit, to the 3/2 minus this to the 3/2, and then we multiply by gamma, and then we multiply by beta with the minus. Globally, we can express the current, the drain current of the MOS transistor in this theory as the difference between two currents, ID prime, ID second. ID prime is the linear parabolic part, and it is written in the second line. ID second is the other part with the terms to the 3/2, okay? At this point, we must complete the calculation by determining the other possible derivatives of the drain current with respect to the other voltages, because the conductance that we calculated was just one of the possible derivatives. It was the, if you remember, GD or GO is the derivative of ID with respect to the drain voltage, okay? Now we must calculate the other two conductances. One is the derivative of the current with respect to the gate voltage. We may alternatively calculate it with respect to the gate to bulk voltage while keeping VSB and VDB constant, or we may calculate it as the derivative with respect to VGS by referring to the source, keeping VDS and VBS constant. Of course, the two definitions are equivalent, and we find that this derivative is equal to beta times VDS. It is indicated with the symbol GM, and it is called transconductance. Finally, we have the derivative of ID with respect to VBS. This is complicated because we must determine the derivative of ID second. That is the only block that contains VBS, okay? The result is GB, and GB is called the bulk transconductance, okay? A very crude approximation for the MOS transistor is neglecting ID second, okay? There are other approximations that are more refined, okay? But just to show one possible approximation, we assume that gamma is small so that ID second is negligible, okay? With respect to ID prime. In this case, we are left with an expression of the drain current that is the standard linear parabolic model that is used as the elementary model for the circuit analysis. The drain conductance has the expression that you see here, the second line. The saturation voltage is equal to VGS minus VD flat band minus 2 phi f. And the threshold voltage becomes a constant, is VD flat band plus 2 phi f, okay? If you replace the expression of the simplified expression of VT in the simplified expression of VDS SAT, you see immediately that VDS SAT can be written as VGS minus the threshold. Also, the bulk transconductance in this approximation becomes equal to 0 because ID second is not there anymore, and VBS appears only in ID second. You remember we have developed a theory that applies only in the linear region, okay? In the off region, we simply say, sorry, in the subthreshold region, we simply say the device is off. But then we have the saturation region that we simply don't know about, okay? But in order to consider the saturation region, we observe the experiments, okay? I think I have some curve somewhere here. The experiments show that if you fix VGS, for instance, in this figure, take VGS equal to 5 volts, okay? And on the horizontal axis, we have VDS, okay? And then you start from 0 and you start increasing VDS. You have the linear region until a point in which the drain current substantially becomes constant. It's not exactly a constant. Still, there is a small slope, small positive slope, but you may think of it to first approximation as a constant. So the linear region goes up to the dot. Okay, this dot is the value of the saturation voltage, VDS sat, corresponding to VGS equal to 5 volts in this figure, okay? Saturation starts from this dot to the right, okay? So extending the linear parabolic model to saturation is easy. We simply state, we calculate the saturation voltage, VDS sat, and then we impose that from that point on, the current is equal to the saturation value because it stays practically a constant. So we include saturation in the simplified model by this very simple trick. And this is explained in this page, in which we have the saturation region. So we are in the condition where the channel is formed. So VGS is larger than the threshold voltage. But we have a VDS that is larger than the saturation voltage. So what we do is we take the linear parabolic model for simplicity. So we neglect ID with 2 primes. In the linear parabolic model, we replace VDS with VDS sat in order to make it a constant. When we do so, we observe that all these parentheses in this simplified model is actually VDS sat already. Okay, so when we replace VDS with VDS sat, we have VDS sat squared. And then we have minus 1/2 VDS sat squared. So by this replacement, we obtain 1/2 beta VDS sat squared. Then we replace it back with its expression. VDS sat is VGS minus VFB minus 2 phi f. And finally, we remember that in the simplified linear parabolic model, VFB minus 2 phi f is VT, is the threshold voltage. So we find a very well-known expression of the current in saturation. Obviously, the current depends only on VGS because the characteristics are horizontal, so they do not depend anymore on VDS, but they do depend on VGS because they grow parabolically, okay, when VGS grows. In saturation, since the slope of the characteristics is essentially negligible, the output or drain conductance is 0. The transconductance is the derivative with respect to VGS. So in this simplified expression, it is beta times VGS minus VT. And of course, the bulk transconductance is 0, okay? And then we have the off state, which we already discussed simply. In this simplified model, when VGS is smaller than VT, ID is 0. So this completes the elementary model of the MOS device, okay? We can also analyze the small signal circuit. For the small signal circuit, we take the more general expressions. We don't make the simplification of abolishing the ID prime part, okay? So we keep it, okay? So we keep the general expression of the current. How can we imagine the form of the small signal circuit of the MOS transistor? Well, we have ID, one current, that depends on 3 voltages. If we make the small signal analysis, in essence, we take the differential of the current, okay? We calculate the small variation of the current as a differential, calculated in the working point. The differential of ID has 3 terms because we have the derivative of ID with respect to the drain voltage times the small variation in the drain voltage, plus the derivative of ID with respect to the source voltage times the variation in the source voltage. And finally, we have plus the derivative of ID with respect to the gate voltage, again, times the variation in the gate voltage. So we have a current that is the sum of 3 currents in the small signal circuit, okay? Because the differential has 3 terms. You will remember we already met this problem in the PN junction. When we have a current that is the sum of currents, that means that the equivalent circuit has branches in parallel to each other. So we expect to have 3 branches and in fact in the equivalent circuit, full equivalent circuit of the MOS transistor in steady state, we have three branches. So this dot here is the drain contact. This dot here below is the source contact everywhere, okay? This dot here is the gate contact, and this dot here is the bulk contact. Of course, the gate contact and the bulk contact are open because there are no current entering the gate and the bulk. The only current is the drain current that enters the drain contact, flows through the three branches in parallel here, and goes out from the source. Okay? There are no currents IG or IB because gate and bulk are open. On the other hand, they have voltages. So also in the variations, we have a small VGS voltage, that is the variation in the gate voltage, and a small VBS voltage, okay? As we did for the bipolar junction, we observed that the output conductance relates the current and the voltage at the same port. So it is a conductance or a resistance, okay? So it must be drawn as a resistance in the equivalent circuit. Then GM contributes to the drain current with the term that is GM times VGS. So this portion of the drain current that flows into this branch is a current that is controlled by the voltage VGS that belongs to another port with respect to the current ID. So this branch must be represented as a current generator controlled by a voltage. The voltage is VGS. And finally, the same applies to the bulk transconductance, because also this transconductance provides a contribution to the current of the drain controlled by a voltage in another port, that is VBS. If we short the bulk and source contacts to avoid the body effect, we impose VBS equal to 0, and of course this current will be 0, so we open this generator if we short the bulk and source contacts. So we come to the very well-known characteristic of the MOS transistor. These curves are for the N-channel device. They have been drawn using the simplified linear parabolic model, taking the threshold equal to 1 volt. You remember the functioning regime is VGS larger than VT. So when VGS is equal to 1 volt, the current becomes 0. Okay. when you have VGS larger than the threshold, then you have a current. If you take any value of VGS, for instance, 4 volts, you have the linear region up to the saturation point, and then you have a constant current in the saturation region. The dashed line is a parabola that is the envelope of all the saturation points. Okay, so you see that the saturation point increases with the gate voltage. Okay, this line has nothing to do. It's a load characteristic of a circuit, so it doesn't really matter in this analysis. We have left behind a number of considerations. You remember at some point we said there is the gradual channel approximation, and in the gradual channel approximation we treat the elementary strip as a parallel plate capacitor, and we shall see whether this is correct. And we also accepted the postulate, so to speak, that in the strong inversion condition we have an ohmic transport corresponding to the condition phi s equal to phi n plus a constant. Okay, so we do not have time to demonstrate everything, but at least something we can demonstrate, that if equation number 3 is correct, that is, if phi s is equal to phi n plus phi f, then the transport is ohmic. Okay, this is easy because we start from the general expression using the monomial form of the current density. So this is true in general, okay? And we have the derivative of phi n with respect to y, and then we also remember that we can replace this derivative with a standard derivative. We don't use the partial derivative anymore. So we have the derivative of phi n with respect to y. This is in the general expression of the current density. At this point, we observe that if phi s and phi n differ by a constant, then the derivative of phi n with respect to y is equal to the derivative of phi s with respect to y, okay? Because both quantities depend only on y. We replace this in the expression of the current density, so to the original d phi n over dy, we replace d phi s over dy with a minus. But what is minus d phi s over dy? Simply is the horizontal component of the electric field calculated at the surface, because phi s is the surface potential. So we simply prove that if equation 3 is correct, then transport is ohmic in the channel. The next lesson we shall demonstrate that equation 3 is indeed correct. So the conclusion is that transport is ohmic in the channel. So we stop now If there are questions, please operate the mic.